Hello everyone, today I'm going to talk about 4D. I'm going to use some inductional method to extend some properties in lower dimension into higher dimension. I think it is pretty useful because in your daily life you're gonna meet some problems that is pretty similar to some problems that you have already solved. If you extend the solution of the previous problem into the current one, you can solve the current problem easily. By the way, I'm not going to talk about time. I'm going to talk about 4D Euclidean space. Firstly, let's talk about the construction of the 4D shape. That is, how can we get a 4D shape? Obviously, we can get a 3D cube from 6 4D squares. But in order to be more clear, let's start from 0 dimension. This is a 0-dimensional shape, it's just a point. We copy the 0-dimensional shape and connect the corresponding point, then we can get a 1-dimensional shape, which is a line. We copy the 1-dimensional shape again and connect the corresponding point, and then we can get a 2-dimensional shape, which is a square. We copy the square and then connect the corresponding point, then we can get a 3-dimensional shape, which is a cube. We copy the cube and connect the corresponding point, then we can get a 4-dimensional shape, and it's called a tesseract. Maybe you are just think this is just 2 cubes instead of a tesseract. Like a line is made by 2 points, a square is made by 4 lines, and a cube is made by 6 squares. A tesseract is made by 8 cubes. I will show you these 8 cubes right now. These are 2 cubes. We construct this tesseract from these 2 cubes. These are also 2 cubes. These are also 2 cubes. These are also 2 cubes. I don't know how to convince you, but they are indeed cubes. I want to show you a better visualization method, but before that, I need to talk about axes. These are 2 axes. The top one is just a common axis, which is very familiar for us. The bottom one is not familiar for us, because it's not in the Euclidean space. The coordinates are exponential. Let's call this an exponential axis. It is very important in the visualization. When you take the interval of an exponential function from 0 to infinity, where the ratio is between 0 and 1, it's gonna be a certain number instead of infinity. That means when the coordinates in the exponential axis goes to infinity, the position of the point on our screen will just be in a certain place. And then the positive part of the exponential axis will have a finite length. Let's call the infinity on the exponential function a disappearing point. In a game called Roller Coaster 2, we have 3 common axes. In our vision, we have 2 common axes and an exponential axis, whose disappearing point is in the center of our vision. When the coordinate of the exponential axis is getting larger, the things are getting far away from us. When we change the ratio of the exponential function, we change the depth of the thing. If we have more than 2 exponential axes, the straight things might be curved. Now let's talk about projection and visualization. Because the light is one-dimensional, the creatures in an n-dimensional space will only receive the vision of n-1 dimension. Imagine we have a one-dimensional space, then we put a creature into this space. Then it should have a 0-dimensional vision. If we put a one-dimensional object into his vision, we'll see a boring yellow point. Now let's imagine a 2-dimensional space contains a 2-dimensional creature. In his vision, we draw 2 axes to represent the coordinate of the real world. The blue axis represents how far away from the river. His vision will be one-dimensional, which is a line. What he will see will like this. The disappearing point of the exponential axis will be the center of his vision. Even if we draw the exponential axis from the different point of the common axis, the disappearing point will still be in the center of his vision. Let's put a square into his vision. What he will see will be like this. Let's remove the transparency, and then he will only see a yellow line. The closest object will cover all other objects. Now let's imagine a three-dimensional creature in a three-dimensional space, and then we draw the axis of the real world again. The blue axis represents how far away from the river. Three-dimensional creatures will have a two-dimensional vision. In his vision, the axis will be like this. The disappearing point of the exponential axis will be in the center of his vision. If we draw the exponential axis from any position in the world, the disappearing point will not change. Now let's put a cube into his vision. What he will see will be like this. Let's remove the transparency, and he will only see a red square. The closest object will cover all other objects. Now imagine this is a four-dimensional world. We put a tesseract into this four-dimensional world. Recall that a tesseract is made from 8 cubes. Again, the blue axis represents how far away from the viewer. This is the closest cube to the viewer, and this is the furthest cube to the viewer. Now in his vision, the axis will be like this, and the tesseract will be like this. This is the closest cube to the viewer, and this is the furthest cube to the viewer. If we remove the transparency, the viewer will only see a big red cube, which is the closest object to the viewer. To draw a conclusion, everything that is far away from the viewer will look smaller because of the exponential axis, and it will be covered by closer objects. Now let's talk about the rotation in four-dimensional world. I will use more mathematical and abstract method to illustrate this. In zero-dimensional world, everything is a point and there is nothing to rotate. In one-dimensional world, we have one coordinate. There is still nothing to rotate. In two-dimensional world, we have x and y so that we can rotate. If we rotate around the origin by theta, the new x and y will be like this. We can swap the plus and minus sign, because sin negative theta equals negative sin theta. This is just a rotation by a negative degree. If we replace the previous x and y with the new x and y, we will finish this rotation. Now let's consider about the three dimension with the new coordinate z. If we rotate around the z-axis, we are just doing the things that we did previously. The z-coordinate will not change in this rotation. If we rotate around the y-axis, it's pretty similar. Instead of we take x and z instead of x and y. The y-coordinate will not change in this rotation. Similarly, if we rotate around the x-axis, we take the y and z-axis and do similar stuff. The x-coordinate will not change in this rotation. Now let's consider the four dimension with an extra axis w. We still have the three rotations in the three dimension. In these three rotations, the w coordinate will not change. No matter the rotation is in what dimensions, there will only be two coordinates that is changing. There are three extra rotations in the four dimension. We can change the xw coordinate, the yw coordinate, and the zw coordinate. The number of rotations is dependent on how many ways can you pair these two coordinates. And thus it is very easy to guess how many rotations is in the 5 and 6 dimensions, and etc. Personally, I think it is more appropriate to describe a rotation as rotation inside of a plane, instead of rotation around an axis. I will show you what the 4D rotation looks like. Let's suppose the w coordinate is the exponential coordinate in our vision. These three rotations will not change the w coordinate, which will not bring the inside cube out. Recall the inside cube is a cube that is far away from us, and the outside cube is the cube that is closest to us. If a cube is facing you, if you are in the three-dimensional space, there's one rotation that will not bring the back face front. That is a rotation which doesn't involve the z-axis. Back to the 4th dimension, I'm going to show you the other 3 rotations that involve the w-axis. I will change the viewpoint so that it is more clear for you guys to understand. This rotation will bring the inside cube out from the left cube. This rotation will bring the inside cube out from the back cube. This rotation will bring the inside cube out from the bottom cube. Don't forget the rotation can have 2 directions. It is hard to visualize 4-dimensional objects because from 4 dimension to 2 dimension in our vision, we lose a lot of information. Thanks for watching.